Schrodinger's cat and its interpretation. Schrodinger's cat is a thought experiment conceived by Austrian-Irish physicist Erwin Schrödinger in 1935. In the time quantum theory was being developed, some scientists wandered from science into the fields of philosophy and stated that quantum particles only collapse to a single state when viewed by a conscious observer. Schrödinger found this concept preposterous and used the thought experiment to explain how some people were misinterpreting quantum theory. In Schrödinger's cat experiment, a cat is placed in a box together with a vial of poison. Above it is a suspended hammer which is attached to a Geiger counter that has a small pile of radioactive substance aimed at it. The box is sealed and left for a certain amount of time until the experiment is over. The radioactive substance has a chance of emitting radiation that will be picked up by the Geiger counter. The hammer would then be released and swings to smash the poison vial, releasing the poison and killing the cat. Since the decay of the radioactive substance is governed by the law of quantum mechanics, the decay is random. The atom starts in a combined state of going to decay and not going to decay. If we apply the observer-driven theory to this case, there is no conscious observer present since no one is able to see what is inside. So, the system stays as a combination of the two possibilities, or as Schrödinger puts it to be, living and dead in equal parts, until it is observed. This state of two possibilities is known as a quantum superposition, which is a result of being linked to a random subatomic event that may or may not occur. However, immediately after opening the box, the cat's state is completely known, and the superposition of the cat, the idea that it was in both states, will collapse into the knowledge that either the cat is alive or dead, but not both. This relates to the quantum theory that quantum particles can exist in the superposition of states at the same time and collapse to a single state upon interaction with other particles. Copenhagen interpretation, the prevailing school of thought. When Austrian physicist Erwin Schrödinger came up with his paradox, Schrödinger's cat, he was criticizing the prevailing school of thought in quantum mechanics, which was the Copenhagen interpretation, by showing how preposterous it will be when scaled up to affect objects in the visible world, and in his case, the cat. The Copenhagen interpretation was devised by Niels Bohr, Werner Heisenberg, Max Born, and other scientists in the 1920s. Until quantum physics came along in the 1920s, physicists expected their theories to be deterministic, generating predictions for the outcome of their experiment with certainty. But quantum theory appears to be inherently probabilistic. The Copenhagen interpretation states that physical systems do not have definite properties prior to being measured, existing in all possible states at once, which is known as superposition. Quantum mechanics can only predict the probability distribution of the possible results that the system can take, which can be shown as a wave function. The act of measurement affects the system, forcing the set of probabilities to be reduced to only one of the possible states of its wave function. Due to the range of observable states the same object could have at each time, explains why quantum particles behave erratically. However, there is a lack of an official Copenhagen interpretation, but there are several components which the majority of physicists agree on. The first component is the uncertainty principle. The uncertainty principle states that there exist pairs of conjugate variables that cannot be both measured to an arbitrary level of accuracy. In other words, there is an absolute cap imposed by quantum mechanics on how accurate a pair of measurements can be made. For example, if we know where a particle is located, delta x is very small. Unfortunately, we will know nothing of its momentum. Thus, delta p will be very large. The next component is a statistical representation. Schrödinger's wave function, psi, provides a thorough description of a quantum system as it yields the probability of an outcome in any given state. The last component is the complementarity concept. Due to light and electrons having on some occasion particle-like behaviors while at other times wave-like behaviors, and it's impossible to observe both behaviors simultaneously, Niels Bohr developed the wave-particle duality concept, stating that to have a better understanding of quantum mechanics requires a description of both wave and particle properties. Next, we'll be talking about the many worlds interpretation. The many worlds interpretation originated in Hugh Everett's Princeton PhD thesis, The Theory of Universal Wave Function, which was published in 1957. According to the many worlds interpretation, the universal wave function exists independently of observation, and there is no wave function collapse, as opposed to the Copenhagen interpretation. This implies that all possible outcomes of quantum measurements are physically realized in some world or universe, and there are very many universes, perhaps infinitely many. The key idea of the many worlds interpretation is that unitary quantum mechanics describes the whole universe. In particular, it describes the measurement as a unitary transformation without using a collapse postulate, and describes observers as ordinary quantum mechanical systems. The many worlds interpretation uses quantum decoherence to explain the apparent collapse of the wave function. Decoherence is the loss of quantum information from a system into its surrounding, in a similar fashion to entropy. Since every system is loosely coupled with the energetic state of its surrounding, components of the wave function are decoupled from a coherent system and acquire phases from their immediate surrounding. For example, in a perfectly isolated system, quantum coherence is maintained. When an observation is made, the system is no longer isolated, and it shares coherence with the environment. This results in the sharing of quantum information between the system and the environment, at which point they are entangled, and the process is irreversible. As the many worlds interpretation interprets the Schrodinger cat experiment, both the alive and dead state of the cat persists after the box is open, but are decoherent from each other. Before the box is open, the state consists of an observer with a possibly dead cat. After the box is open, the state splits into two states, an observer with a dead cat and an observer with a live cat. By opening the box, the observer becomes entangled with the cat, so the observation of the cat state and the cat state correspond with each other. Quantum decoherence ensures that the different outcomes have no interactions with each other. This prevents the simultaneous observation of multiple states. A variant of the thought experiment, known as the quantum suicide machine, was proposed by Max Tegmark in 1998. It examines the Schrodinger cat experiment from the point of view of the cat, and by doing so can falsify every interpretation other than the many worlds interpretation. By conducting the experiment multiple times with the observer in the box, there is a world where the observer survives all iterations of the experiment, no matter how many iterations are carried out. The survival of the version of the observer is necessary. This contrasts the Copenhagen interpretation, where the survival probability of the observer will tend towards zero as the number of iterations increases. However, this experiment may not be entirely applicable in the real world, as dying is not a binary event, as in the thought experiment. Instead, dying is a progressive process with a continuum of states of decreasing consciousness. We hope that you have learned more about the Schrodinger cat experiment and its interpretation. See you next time.